In match problem 2, we're after the same goal as match problem 1. We want to identify any local maxima or minima, but now we're given functions that aren't restricted to some specific interval, so we're just considering the entire domain of the function. So we want to use the second derivative test whenever that applies. That's going to be our first approach. Unless we run into that case where it's inconclusive, then we'll reference back to the first derivative test. So the first thing we need to identify are any critical values. So we'll start by taking the derivative of our given function, which is 3x squared minus 18x plus 24, which can be factored as 3 times x minus 2 times x minus 4. So we'll take that first derivative, set it equal to 0, which is going to give us two values, x equals 2 and x equals 4, as our two solutions there. And we'll go ahead and calculate the second derivative as well. That's going to be 6x minus 18. So now what we do is evaluate the first and second derivatives at both of these values. Really, we can skip this step of evaluating the first derivative of those two values because we already know that f prime evaluated at 2 is going to give us 0. F prime evaluated at 4 is going to give us 0. So really, we need to look at the second derivative and evaluate that at 2 and at 4. So 6 times 2 will give us 12, minus 18 will give us negative 6. Second derivative evaluated at 4 will give us positive 6. So negative 6 obviously is less than 0. Positive 6 is greater than 0. So since the second derivative is less than 0, that means we have a local minimum, and that's going to occur at f of 2. Since our other result, the second derivative is greater than 0, we have a local maximum, which is going to occur at f of 4. Now we want to do exactly the same thing in part B. So we'll start off again by finding the first derivative of our function, which will be e to the x minus 5, which tells us that e to the x is equal to positive 5. So now to solve this, what we'll have to do is go back to a method that was similar to solving values with the continuously compounded interest formula. We'll take the natural log of both sides. The natural log of something, we can bring that exponent down as a factor in front, and then the natural log of e is just 1. So we get x equals the natural log of 5. So then we'll find the second derivative, which is just e to the x. So we only have one critical value to consider. So we'll take our second derivative and evaluate it at the natural log of 5, which will give us e to the natural log of 5. So e and natural log always cancel each other out. They're inverse operations. So that's just going to give us 5, which is greater than 0. So our second derivative evaluated at that point is greater than 0, which means we have a local minimum at f of the natural log of 5. In part C, again the same idea, we'll take the first derivative, which will be 60x to the 5th minus 120x to the 4th plus 60x cubed, which will give us 60x cubed times x minus 1 squared. Setting that equal to 0 gives us x equals 0 and x equals 1 as our two solutions. So our second derivative will be 300x to the 4th minus 480x to the 4th plus 180x squared. So we'll evaluate the second derivative at 0, which will give us 0 minus 0 plus 0, or just 0. And we evaluate the second derivative at 1, which will also give us 0. So we evaluate the second derivative at each of those two critical values. They're both inconclusive. So in order to classify these as minimums or maximums, we have to go back to the first derivative test. So the first derivative test tells us that we would construct a sign chart for the first derivative. We know at 0, we encounter a 0 for the first derivative. At 1, we encounter a 0 for the first derivative. And then we would just choose some test points in between. So if we go and evaluate the first derivative at -1, that result would end up being negative. If we evaluate it at 0.5 or any value between 0 and 1, the first derivative is going to be positive, and for any values greater than 1, the first derivative is going to be positive. So again, we're just taking those test points, plugging them into the first derivative to see what result we get. And then we just need to interpret those results. So at f of 0, our function changes from decreasing to increasing. So f of 0 is a local minimum, because again, we've got a function that's decreasing. We hit some point and change directions to increasing, so that would be a local minimum. Here we have a function that's increasing, levels out, levels out, and then just continues increasing. So there is no local extrema. Or local extremum, which is just the singular version. So there is no local extremum at f of 1. It's not a local minimum, it's not a local maximum.